thank you very much, Jeff, for this nice introduction. Yeah. And it's hard to express how happy I am about this collaboration, and I really have to say I'm very impressed how fast you made this working, and just 1.5 years after the relaunch of the center, and you made everything with almost with the speed of light. So I was very impressed to see the laboratory here, and we are now really ready to do a lot of good work here for the benefit of industry partners, of course also for research. I also have to thank a lot of people that this was possible. It's always dangerous to tell names, but I think it's easy to really thank Radenka. Without her it would not have happened. Also Kazem, just sitting beside us. Thank you very much for your help and for your patience with this. The starting was a little bit difficult, but now the speed is really impressive, and I'm very confident that we can really make something good out of the whole collaboration. Also have to thank my people, of course, Markus White, who is responsible from Fraunhofer side, also Ingold Vogt, he is here as well. So now I only have a few minutes, 15 minutes, but a lot of slides, so I will rush through the slides. And I'm already in the middle of the presentation, I see, but I have to start again. And General Counsel Menzenbach already mentioned Fraunhofer, so I can skip almost the first slide because she already explained Fraunhofer. You see here the latest figures, so 72 institutes, pretty uniformly distributed all over Germany, roughly 25,000 employees, total budget of 2.6 billion euro. And I think important is that this budget doesn't switch, that roughly 70% of this budget, what can I do? Sorry. So Fraunhofer only has technical problems with slides. Usually in projects, no technical problems occur. So 70% of the budget comes from work with industry. So we get certain incentives when we earn money from industry doing projects. We get a certain incentive, and then the base funding depends on this as well. So our mission clearly is to applied research. We do research for money, and we know how this works and how to provide results to industry. Now to my institute. So we are the IKTS, Institute for Ceramic Technologies and Systems. Roughly 700 people, budget of roughly 60 million euro. And we are the fourth largest Fraunhofer Institute, by far the largest one in the eastern part. And we cover ceramics in a very broad sense. So this is a busy slide, as you see here, because it's the attempt to summarize our core competencies on one slide. The basic message is we have two major divisions. One is structural ceramics, so we make all kinds of fancy components for machine engineering, automotive industry, medical applications. And important is we cover the whole value chain. That means we start from the synthetic ceramic materials, and then we go up the whole chain to make components, as you see here. And the specialty of Fraunhofer is we cannot only do this in lab scale. So if our partners need 100,000 or maybe even 1 million parts, we also do pilot scale developments to test markets and things of this nature and to share risks. The other division is functional ceramics. This is even more important. Not many people are aware that the whole world of electronics, for example, is a ceramics world. So every capacitor, every resistor, every coil, every microchips consists of ceramic materials. Also, ceramics can have nice ionic properties, so that means battery technology, fuel cells, a lot of energy technology also involves ceramic materials. And this is, of course, also an important field for us. And in between, we have a big group, roughly 200 people working on non-destructive evaluation, testing technology, which is very important to come up with new kinds of sensors for digitalization technologies. I will come back to this later. Before I talk about the membrane technology and environmental technology that we are focusing on this center, I would like to mention that we cover energy and environmental technology in a much broader scope. Here some of our core development subjects are shown. So we do a lot of work in the field of conventional combustion engines. I even don't give up on the diesel right now. We do a lot of development to make it clean and even more efficient. Renewables, of course, is a big issue. Photovoltaics, also wind energy, energy harvesting. I have no time to talk about this. I will talk a little bit about the battery and fuel cell technology that we are developing. And of course, in this center, we will focus on the membranes and porous ceramics for water treatment, but also other kinds of environmental issues. Yeah, what are we doing? So what is our core competency? I will illustrate this with one value chain, as you see here. It always starts to the left here with a ceramic powder. And this is already a big know-how, how to tweak the properties of these powders, to make a good flow, to make it very uniform, to make a powder that can be used in the next process steps. And out of this powder we make a slurry, and then we deposit this slurry on surfaces, and out of this we stack some surfaces and we make systems out of it. In this case you see a lithium cobalt oxide powder, can also be other kinds of powders which are used for batteries. So lithium-ion battery technology, for example, is a classical ceramic technology, and we do a lot of work in this field. So this is classical ceramic technology. Another example, you see the same again. Ceramic powder, then we make a slurry out of it. This ceramic powder can have every thinkable physical or chemical property. It can be insulating, it can be semiconducting, it can be conducting, piezoelectric, ferroelectric, ferritic, also magnetic. And then you can make a paste and ink again out of it and print this property on surfaces in order to functionalize these surfaces. This is very established technology. For example, a lot of microelectronic devices, sensors, depend on this technology. So you can print these ceramic paste and materials on ceramic substrates, you stack it, and then you come up with three-dimensional integrated electronic components or sensors, as you see here. One example is just shown here. This is a multi-layer ceramic capacitors. I do not know how many of these capacitors are produced each year. Several trillion, so millions per human being. So that is a real mass production. Sometimes there is this rumor that ceramics is too expensive for applications, but this is not true. This is the most robust and most productive technology you can imagine, and this is really very much established. And we use this platform for electronic components and also to make a lot of sensors. Here you see just some examples in the top row here of some physical sensors that we are developing. Can be pressure sensors, acceleration sensors, flow sensors, temperature sensors, acceleration. So here you see an acceleration sensor that can cope with 100,000 G, showing how, with what extreme conditions ceramic components can cope. Has some military applications, unfortunately, here, yeah. But for us, it's very important to use this technology to develop sensors for Industry 4.0 applications or Internet of Things applications. When you go into this digitalization world, it's important that you collect data. And it's better to collect these data at the place where the action takes place. So where you have high temperatures, you have harsh chemical environments, you have a harsh strain or something like this. And this is a big field in our institutes to make new kinds of sensors which can cope with very harsh environments and to use this for all kinds of digitalization technologies. This is very important. And then, of course, we want to combine this. I was briefly talking about the battery technology. So we have a lot of know-how how to make batteries. But we also have this digitalization know-how to how, including software engineering, artificial intelligence approaches, and the combination is excellent because our goal is not only to improve process for battery manufacturing, for example, but to come up with complete digitalization processes. For example, we are pretty proud on this, to help that CATL, it's the biggest battery company in the world, Chinese-based, came to our country, and they were not so much interested in our battery materials know-how. They were much more interested in digitalization, because they say, when we come to such a high-level country, we do not just want to copy a process, we want to come up with the best process in the world, and for this we need this digitalization technology. So this combination of materials know-how and the sensor and digitalization know-how, I think this is pretty unique. And this is something we also would like to use for membrane technology. Because here again, we cover the whole value chain. You see here the ceramic membranes that we are developing. We start with ceramic substrates. You see this to the left can be planar substrates made by tape casting, pressing technology, or tubular substrates made by extrusion technology, for example. These substrates are porous, have a microporosity, and then by our printing paste technology, we print the active membrane layers on top. And they can have a porosity down to the sub-nanometer regime. And here this printing technology, that what we learned from microelectronics, from the battery technology, is applied to make functional membranes. This is what we want to bring to the US. It's, believe me, that is really very specific core know-how that you need. And out of this, we make then modules, so membranes, 1.5 meter high, or in the US I have to say 5 foot, I think, yeah. And we can assemble this to make modules and then up to really demonstration units. And this is something we would like to do along with Jeff. So we can supply these membranes in any quantity you need. So we would be happy to hear that you need 100,000 of these pieces. We will send it to you, and then we will make nice demonstration units according to the needs of the US market. So this is our core competency, and of course there are already some nice examples. Ingolf Vogt will have a talk, and he will go much more in detail. This is an example of development along with Shell company for oil sand refinery. The beauty about this ceramic membranes, they can cope with these harsh environments. In oil sand refinery, you have particles, you have critical chemicals, and it's not so simple to really treat these polluted waters that are generated. And by this technology that we first demonstrated in feasibility studies, now in pilot structures, we see that we really can purify or treat this processed water here and cope with these environmental issues. This is just one example. More examples are shown here. So we make these membranes out of a lot of different kinds of materials. You see here, for example, oxides, all kinds of oxide ceramics that can have an amorphous structure. And here we make sure that we have a nanoporous structure. We also use zeolite. Zeolites have this cage structure, and the cage opening can be used for filtration as well. There are different zeolites with different cage structures, cage openings. We can use graphites, and here the lattice distance can be used for filtration purposes. Nowadays you should not say carbon or graphite, you should say graphene. It's much more fashionable, I think, yeah? And you get more money if you tell, but it's still graphite, yeah? And can use this for filtration as well. And even dense layers can be used. This mixed ion electron conducting materials, perovskites for example, that also can be used for separation of gases, for example. This here is a certain perovskite we developed for oxygen pumping and oxygen generation. So this is how these layers look like in applications. So these oxide ceramics are used for a lot of wastewater cleaning application. Here you see a unit that was used for textile treatment to produce water coming up as textile production. For the zeolites, we here developed a unit that is able to separate the water out of bioethanol. When you produce bioethanol, you still have a lot of water in it, and now you use distillation processes which consume a lot of energy. When you use these membranes, you need much less energy to purify bioethanol. Or these carbon materials, or graphene, that allows to purify biogas. Biogas consists roughly of 50% methane, 50% CO2. And this membrane can separate the CO2 out of the methane. You come up with almost natural gas grade gas then that you can put into a natural gas pipeline then. And here you see an example for this mixed ion electron conducting perovskite structures, and unit that we developed and also presented this on several Hannover fairs already. If you operate it, then it separates the oxygen out of air. You see it's now in operating, and here the oxygen is produced. This is a cigarette. It also allows you to smoke very fast using this technology, but also to produce pure oxygen for hospitals, for example, but also in large quantities. It's also very nice technology that we want to bring to the market. We also develop other kinds of membranes. So when we talk about these perovskites, so this is a mixed ion electron conducting membrane. We also produce membranes that can only conduct oxygen. And one important application is fuel cell technology. Here you see solid oxide fuel cells. This is a ceramic type of fuel cell based on this membrane technology. And this is also something for long term that we would like to bring here to the center. And based on this technology, we develop whole fuel cell systems that can be operated, switched on. They are certified for demonstration. And the use could be autarkic power supply of single-family homes. So you can operate these fuel cells with natural gas. That's the beauty about these high-temperature fuel cells. They don't need hydrogen. They can also be operated on hydrocarbon fuels, such as natural gas. And they have extremely high efficiency. Here you see an efficiency of 100%. The reason is that we produce power, but also heat, high-level heat, which can easily be used. And if you use both the power and the heat in such combined heat and power applications, then of course you have an efficiency of 100%. And we think when you combine this with battery technology, with PV panel, you can come up with complete new kinds of approaches how to make autarkic power supply for homes. There's also big demand right now in Europe, and I think this is also promising technology. And we have all the units running right now. Also, range extender is an issue. I have no time to mention this. The beauty about this fuel cells, membrane-based fuel cell, is they can also be operated in the reverse mode. Yeah? Then you don't call them SOFC, then you call them SOEC, solid oxide electrolysis cell. And the beauty about this fuel cell, when you have power, maybe even excess power, when you have a lot of renewables, of course, you can convert water steam into hydrogen. But this fuel cell can do more. It can also convert CO2 into CO. So you can also electrolyze or get rid of CO2 actively. Yeah? That means when you have a CO2 source, for example, out of air, and hydrogen, you can make synthesis, a gas, we call this co-electrolysis. And out of the synthesis gas, which is H2 plus CO, you can make valuable materials. You can make artificial fuels. It's hard to compete with Saudi Arabia right now here, but you can also make higher added value stuff, olefins, alcohols, waxes for cosmetic industry. So this carbon capture and usage, this is a big thing that we are working on, and we combine these fuel cells, for example, this new kind of Fischer-Tropsch technology. Other applications of this, just one point here, when I talk about this, here's a comparison of different electrolysis technologies, which is very important for future kind of storage. When we at any time come to hydrogen economy, or when we have a lot of renewables and we are able to store huge quantities of energy, you need some kind of electrolysis. And there are different kinds of electrolysis technology, alkaline electrolysis, another kind of fuel cell, PEM electrolysis, and then this SOEC. We work on all of these technologies. SOEC has a big advantage when you have temperature, a temperature source in industry, for example, because then you need roughly 3 kilowatt hours power to make 1 norm cubic meter of synthesis gas. 1 norm cubic meter synthesis gas has more energy content of 3 kilowatt hours. That means you have an efficiency of more than 100%. Physically, this is critical, what I'm saying here. Honest. The reason is why I just gave the power input here. So what kind of power you need. I did not mention the heat. So this technology also converts heat into gas here. And when you have this heat source, then this is the most clever technology and the most efficient technology for the storage technology. And really something we are looking into it. And finally, the big picture is to combine all of this stuff. Yeah, to really come up with closed cycle technology, to use waste, convert this by gasification technology into power, separate the CO2. For this, for example, you need the membranes. Use this for this co-electrolysis to make valuable materials, also to generate hydrogen or e-fuels for future technology. You see here we use the oxygen generator, we use our membranes, we use our fuel cells. Just to give you a flavor, so I could talk at least about this slide another 15 minutes or something like this, but this is something, the scope that we see. So we will start with this membrane technology and water treatment, and I think we have excellent ideas how we will continue, but finally, in 3, 4, 5, 6 years, I would love to to extend the whole scope into this technology, which I think has a lot of potential for future, to really make everybody's talking about climate change and environmental issues. We want to provide solutions here, solutions which even have economical benefit and which allows us to make money and to export some stuff. And here I think we have excellent solution, and I'm happy that we can do this together in future. And I'm very confident and very happy about this collaboration. Thank you very much for your attention.